Good morning or good afternoon. It depends on whatever you are. Today I'll be talking about transformer testing and in particular core loss and excitation current. So core loss measurement, some people call it core losses or no load losses. And these losses are caused by the excitation or energization of transformer core. Transformer is energized but is not loaded, so it's not connected to a load. Transformer is like an iron or steel core reactor since one side is open. So transformer has a primary side and a secondary side. So one side is energized, the other side is not energized, is open. So no load losses, so they have core loss or core steel / iron losses, dielectric losses, winding losses. Core steel, because the core is energized, so there will be subject to some losses. Dielectric losses, so uh, the conductor or the copper or aluminum, that makes the turns of the windings. They have insulation from turn to turn and phase to phase. But that insulation is not perfect, so some current is going to leak, causing some heat or watts basically. And the winding losses, because you energize one side, so they're going to be subject to current, the excitation current, so they're going to cause some losses. But we know that iron losses or core losses are very, very big. They are way bigger than dielectric plus I squared R losses. Iron losses, they are made up of hysteresis, what we call hysteresis, and eddy losses. Hysteresis is a function of the flux density, B. Eddy losses is a function of the RMS voltage that's applied. And if you take the Faraday equation and you carry out the calculation, you will come to the maximum flux density. Bmax is equal to the RMS voltage divided by 4.44 times F is the frequency. In the United States it's 60 hertz. Some other parts of the world is 50 hertz times N, which is the number of turns of the winding that's energized, times A, the cross-section area of the core. And note 4.44 is nothing else but is the square root of 2 times pi. So square root of 2 times 3.14. So just kind of quick reminder. So this is a core and coil assembly. So you have the core, the windings, you have the core, and obviously you have the core clamps holding the core together so it doesn't collapse because it's made up of laminations. And here's a core. So you have the core limbs or core legs where the windings are wound around, and you have the core clamps to hold the top yokes and the bottom yokes of the core together so they don't fall apart basically. And you have some tie rods, so some manufacturers might use tie rods. There are different technologies. So when you energize the transformer, so the core is subject to the excitation current, which causes some losses. And also the winding that's energized causes some losses due to the I square R effect. Since the winding is made up or made from copper or aluminum, small transformers might have aluminum windings. So why are core losses measured? Core losses may be guaranteed, some customers might ask for core losses to be guaranteed. Small distribution transformers with low voltage less than 600 volts are subject to DOE efficiency, Department of Energy efficiency. This is only applies to the United States. So, and these are small transformers like pad mount transformers you see by stores or restaurants, or pole mount. They're mounted on a pole, so they're small. They look like a cylindrical can. So and they have to stamp on the nameplate DOE compliant. So it's like a must. They have to. If the transformer does not meet DOE efficiency, so basically the Department of Energy publishes efficiencies or efficiency values, that they have to meet per kVA, or so they have certain criteria. And if the transformer does not meet that deficiency during the testing, basically the manufacturers will have to remake the transformer, basically scrap that transformer and make a new one, because it's a must. It's not something they can negotiate. Large transformers are not subject to DOE efficiency, but customers might specify max core losses, basically losses not to exceed. They may tell the manufacturer during the bidding process, these are core losses we would like you not to exceed. Customers might ask manufacturer to quote and guarantee core losses. Some customers, like before they send the RFQ, the request for a quote or for proposal, they might ask manufacturers to quote core losses, the core losses that the transformer will see when it's energized, and those losses, they have to be guaranteed that they will be met during testing. Guaranteed core losses are or could be subject to a penalty. So basically the customer, when they set the request for a proposal, they may tell the manufacturer, I would like for you to quote core losses and guarantee that when the transformer is tested, those losses will not be exceeded. And if they are exceeded, I'm going to charge you this amount of dollars per each kilowatt over the guaranteed core losses. Core losses are required to perform heat run or temperature rise tests, because you need to know what losses, total losses, you would apply to run the heat run test. Total losses basically are core losses plus load losses. And I would recommend watching the previous videos where I talked about load losses, how they are measured, and so on and so forth. So for IEEE designs, the tolerance is 6% for the total losses. And again, total losses is core losses plus load losses. And IEEE tolerance is 10% for core losses. So, but again, it depends. So the customer might tell the manufacturer, quote and guarantee the core losses. If core losses are exceeded, during testing, that doesn't mean that there's something wrong with the transformer. It's just basically the customer might elect to apply the penalty, But obviously, if the core losses exceed 10%, then manufacturers, they have to kind of investigate, make sure that there's nothing wrong with the transformer. So, and manufacturers, they have experience, they know, when core losses are exceeded, if something is questionable, and they will do further investigation. So core losses are also, like I just stated, they are a quality check, because when you energize the transformer at no load, basically is not loaded, you have the core is excited, and the core is made up of laminations, and those laminations, they have insulation. It's a carlite insulation, and so there is basically insulation from one lamination to the next lamination. If that coating is somehow scratched, basically you can have a short circuit from lamination to lamination, which will cause circulating current, and it will basically heat. So that's one thing. The other thing is, or probably uh, the design engineer said this is how much core or how many laminations you have to use to build the core. Probably the operator made a mistake and forgot to put the correct number of laminations. So the the losses will be a little bit higher. So it can catch workmanship issues, also uh, material problems too. Like I was saying, if the coating comes from the core material or core manufacturer comes like with some kind of damage, it will be caught during testing. Then you have the winding that's energized. You have copper, for instance. Uh, probably some turns are shorted during the workmanship. They were shorted, so it will show up as a high excitation current because you will have circulating current. Or probably you have an open circuit somewhere, so you have some turns out of the circuit. So you're gonna basically, it's a good check. Again, as I stated in previous videos, the transformer goes through a lot of tests, you know, and all these tests, they complete each other, so they're good for diagnostics. It's kind of like when you go to the doctor, the doctor doesn't do just one test and make a decision. They might say, okay, go do this test, go do this scan, go do this, so then based on all those tests and scans, x-rays, then they can make some kind of, decision. So the same thing with the transformer. So core losses is just one test, but when applied with other tests, it will give the manufacturers an indication if there is something wrong with the transformer. So how are core losses measured? So basically you have, again, just for simplicity purposes, I'm just assuming this is a 2-winding transformer. Obviously, you have auto transformer, you have 3-winding, 4-winding, 6-winding, uh, you have delta Y. So there are lots of combinations. But for simplicity, I'm just assuming this is a grounded Y, and it's a 2-winding transformer. But obviously, the concept is the same. Once you understand the concept, then it's not that hard to understand, to apply the same concept to other types of transformers. So rated voltages apply to one side, typically low voltage windings. That's because you're going to apply voltage. It's preferable to apply to the low voltage to the low voltage winding, because let's assume it's GSU, for instance, at 20 kV to 345 kV. Why would you subject the transformer to 345 kV when you can subject it to 20 kV? It's a lot easier on the transformer. So core losses is kind of the opposite of load losses. Load losses, you apply or you circulate rated current. In that case, you circulate rated current to the high voltage windings, because high voltage means low current. In this case, low voltage means high current. So, and the windings that are not excited, they are left open basically. So you can see so here are the terminals. So you have X1, X2, X3. You can see they're connected to the source basically of the voltage. And the high voltage winding H1, H2, H3, they're not connected to anything. They're left open. So the non-tested terminals are basically bushings, are left open. Measured at the same time are core losses in watts, excitation current in amps. So basically when you apply the voltage, its excitation current is the current that will flow in the windings. Actual applied voltage. Sometimes, say again, If it's a 12 kV winding, sometimes it might be hard to apply 12 kV, so it might be less than that, but they will measure that. So once the core losses are measured, they need to be corrected. So core losses are measured at temperature, Tm, during test. So whatever the temperature happens to be, IEEE reference for core losses is 20 degrees Celsius. Basically, you measure the core losses, then you correct them to 20 degrees Celsius. But obviously, customers they can specify what they want. They can specify 85 degrees Celsius or whatever. But we'll see in the following examples why IEEE, for instance, chose 20 degrees Celsius. So here's the formula that you use to correct the core losses from the temperature during test to the reference temperature. So P is basically just losses at the reference temperature is equal to the losses measured at the test temperature plus this factor here. So it's 1 plus the test temperature minus the reference temperature times a constant K. Tref is the reference temperature, 20 degrees per IEEE, or it could be a different temperature per customer spec, whatever the customer wants, basically. Pref is the losses at reference temperature, 20 degrees Celsius per IEEE, or at whatever temperature the customer wants the loss to be corrected to. PEM is just losses at test temperature. K is an empirical coefficient for a grain-oriented core. Typically, it's 0.00065 is used if the actual value is not readily available. So this is most manufacturers use this value. Obviously, if you have an actual value that's developed by empirical data and testing, obviously it's preferable to use it. But if not, this value is typically used. So here's an example. So if we assume this is a 27/36/45 MVA transformer, the high voltage is 138 kV grounded Y, low voltage is 13.2 kV grounded Y. The core loss penalty is $5,000 per 1 kilowatt if it exceeds 18 kilowatts at the base MVA or on-end MVA or 27 MVA in this case. So basically during the core losses, the temperature was 23 degrees Celsius. Core losses were measured at 16.4 kilowatt. The excitation current per phase. So phase A is 1 amp, B phase is 0.6 amps, C phase is 1.1 amp. So the average is around 0.9 amps. So notice you have 3 phases, but the middle phase typically is lower than the other phases, and that's because the middle phase, if you draw the core, the middle phase has a shorter magnetic path. That means a lower, it takes less current than the outer legs basically to excite the core. Rated current, so if we take the base MVA, 27 MVA, at which the core losses are guaranteed, divided by square root of 3 times the line-to-line voltage of the excited winding, which is the low voltage winding. So it comes to 1181 amps. Excitation current in percent, you take the average 0.9 amps divided by the rated current. So it's about 0.076%. So excitation current is very small. And that's because we're using an iron core, which is a magnetic steel basically. So it takes less current to excite the core. If you introduce a gap in the core like they do for certain reactors, to change the reactance basically, then it will take more current to excite the core. But since it's a magnetic core, so the excitation is really very small. So basically, in this case, I'm just keeping the same information just for easiness of reference. But generally speaking, the excitation current is 1 to 5% for small transformers, and between 0.1 to 0.3% for large transformers. So it's very small. So now if I apply the formula that I showed before, so the core loss is at reference temperature. In this case, I chose 20 degrees Celsius. So the measured loss, core loss, is 16.4 kilowatt times 1 plus test temperature 23 minus the reference temperature, which is 20, times the empirical coefficient. So I'm just using the value that's used by industry-wide, basically 0.00065. So 16.4 kilowatt times 1.00195 kilowatt, which comes to 16.43 kilowatt. So it's a small. So it's this calculated value is smaller than the guaranteed value, which was 18. So the penalty does not apply in this case. Notice since the test temperature is kind of close to the reference temperature, the core losses didn't change a lot. Now we will correct the measured core losses to 85 degrees Celsius. So all this information here is I'm just keeping it just for reference. So the core losses at 85 degrees Celsius is 16.4 times 1 plus 23 minus the reference temperature. In this case, I'm choosing 85 times the constant. So you see the coefficient went down, making the core losses to go down as well. So 15.74 kilowatt. So if I take the ratios, it's about 4%. So notice the test temperature is 23 degrees Celsius. When I chose the reference temperature as 20, the core losses didn't change a lot because the temperatures were close. But when I went from 23 to 85, the core losses went down by 4%. So that's one of the reasons why IEEE, for instance, recommends the core losses to be corrected to 20 degrees Celsius. In other words, core losses decrease as temperature increase. So that's one takeaway from this small exercise. So that was it all for this video. So if you want to see more videos, I would recommend going to Engineering Simple. Thank you for watching and have a great day.